Morning Year 14, welcome to the weekly review where we will be looking at data structures, stacks and queues. But before we begin, can I please reiterate the importance of attending the live lessons, of completing the work and submitting it to meet deadlines. As you're aware, WJC have cancelled the examination process and the grade will be awarded by the centre. In order to make sure you get the highest grade possible, you need to be submitting the works and allowing me to mark it. That includes our coursework and our theory work that we'll be doing. So we will begin by reviewing stacks and queues. Right at the beginning of the lesson on Monday, we looked at this concept that a new primitive data type were being introduced called a pointer. So a pointer is a data type that stores a memory location. So pointer 1 equals SCF3, whatever, blah, 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 some type of hexadecimal address that represents a memory location. And these are key to understanding how stacks and queues work. So the basics of stacks we discussed in the lesson, that we'll call a last in, a LIFO, a last in, first out structure. Again, thinking of your stack of pancakes or stack of books on a teacher's desk. If you were the first person to submit your book, it's at the bottom of the stack, and the last person is at the top of the stack. Hence, the last in is the first out. And this idea that it needs a pointer, this idea, a data type that points to a memory location. And the two operations we talk about: parsing, adding data onto a stack, and popping, removing data from a stack. And finally, even though it says it's a dynamic structure, we set a contiguous block of memory aside in order to use as a stack. It's not infinite. It eventually can reach its potential or reach its maximum, and that's what we have this idea of. You're familiar with the concept stack overflow. So if we look at programmatically, just to review, and we can see a stack, we're going to look at algorithmically what were the processes of popping, of adding to and removing. First thing you will see here is this idea. I'm trying to simplify a very abstract concept of a stack here. A contiguous block of memory, and some of the memory locations are empty, but it cannot grow. If I try to parse on data that is greater than the length of this memory stack, there is a stack overflow. So let's look at the idea of popping, removing it. And algorithmically, if there's nothing in the stack, you cannot pop from it. So that's the first thing. So I've coded that. If not my stack, sorry, if it's empty, if you're getting that, if it's not equals to empty, then look, what we can do is we can pop it. So I'm looking at the reverse logic of that. So if the stack isn't empty, what we can do is find where the top pointer is, and that tells us where the last date item is. And in this case, top pointer is 3, not 1, 2, 3. It's Diana. And we can return that, and we can overwrite her with empty, and we decrease the pointer value, so it will now point at Connor. So when I run that, if we look at this here, I'm going to print the stack, and then I'm going to pop it, and I would expect Diana to be popped. And we run it. If you just look at the first two codes, there we go. Diana was on the list, but she's been popped, and you can see now that this array is empty. So the next thing is parsing onto the stack, and again we've got to consider the algorithm. If the stack is full, you cannot parse onto it. You would return an error, stack overflow. So there's the first part. Look, if this pointer is less than the length of the stack minus 1, what we can do is we can pop something on. We can take in data, and we can go to the pointer, we can increment the pointer and slot it into the stack, else there's an overflow. So if we look at this idea here, we're going to call here parse my stack Eve and print it, and you can see in the output that Eve has been, Diana was popped and Eve was being placed into it. That is the basics of stacks. Let's look at your homework question. So given the consent that the original stack is going to be 3, 4 and 5. That's the order that they were popped onto the stack. The question here is, what happens when there's a pop? Well, for popping, we're popping 5, because remember, these are a last in, first out. And it says here, 5 the last. So 5 is popped out. Now we're parsing 7, so I'm going to have 3, 4, 7. Now I'm popping. 7 was the last in, it's out. I'm in 3, 4. Now I'm parsing 8. 3, 4, 8. Now I'm pushing 9, 3, 4, 9. 5 marks, 1, 2, 3, 4, 5 out of 5. And the next concept we looked at was a queue. And if we go back to our algorithms for a queue, queues is what we call a first in, first out structure. It's like the queue processing at the canteen. This idea, if you look at my queue, Sam is at the head of the queue. The queue requires 2 pointers. We need to know who's at the front and who's at the back, the pointer front and the pointer back. So if I'm dequeuing or I'm popping something from the queue, I need to pop from the front. But if I'm parsing data, I need to parse onto the rear. So algorithmically, if you think about popping, it's the same as the stack. You cannot pop from an empty queue. So the first thing you do is check if it's empty. And then if it's not empty, we can follow into our algorithm. What we're going to do is get the pointer front. That is my queue 0. It's going to be the first pointer. Override it as empty and increment this. So the pointer will go up to 1. Parse, again, think about it algorithmically. You cannot add something into a queue if there's no space. So we've got to check that there is space, and if there is space, what we can do is we can take the data, find out where the back pointer is, increment the back pointer, and then append the data into it. So I put the data in, then increment the back counter, and if we run this, run queue, what we have here is we're printing the original queue. It ends with Edward, as you can see here. We're popping, and it should be popping off the front. So Sam is gone and it's been overwritten by an empty allocation. Then what we're doing is we're pushing Frank on, and you can see Frank has been here and the back pointer or the rear pointer has been implemented. So that comes to your homework question. And in order to score 5, we needed you to refer to the diagram. So if we look at the diagram, we've got the 2 pointers. You need to make reference to the front and the rear pointer. We've got one empty location in this queue. You've got the indexes of the data structure, and then we've got the actual data. So explain, referring to the diagram, what happens when attempting to add. So the first thing that we're doing is adding, if there is space. So we're going to check that there's space available. So I'll just summarize that, say check if there's space, and if that evaluates through, how are we adding into this? Well, the first thing that we're going to do is increment the rear, and we are going to say that we've called all those called queue, the queue rear, we're going to write in the data that's been parsed to it. So if you're putting that in, say, extended English, what you're going to say is, in this diagram, in order to add data to it, we need to increment the value of the rear pointer, hence that would become 5, and the data would be written to space 5 within this location. It says, what about removing it? And we consider this, if we want to remove, we have to remove from the head or the front of the queue. So what we're going to do is go to the queue, and the reference is going to be the front, and we're going to overwrite that, or we're going to return it and overwrite that with empty. So again, we'll look at, well, I don't have a model answer, but you should be referring to this diagram and the use of the pointers, how they are incremented and decremented to score full marks. Folks, it's important that you're reading through all the notes that have been uploaded on this in Stacks and Queues, because next week we'll start links lists, and again there'll be a question that you're expected to complete by the end of the week. So take care, and I'll chat Monday.